Now, I'm going to do a better job. Well, I hope to do a better job.
You know Bob Ross, but...
Man, my hair's not quite the same. All right, now, this is going to represent the 55 milliliters of the hydroxide. I am going to put, I'll do it, 3 hydroxides. This is going to represent the iron 3. I'm going to put 1 of those. What are we going to do with those 2 solutions? We're going to add them together to produce a larger volume. Actually, I'm going to add more stuff in here. This isn't going to be an exact representation of this. It's not going to be an exact representation. Okay. Now, and this, if I recall, was like, wrong color. 35 milliliters, is that right?
Yep. Yeah.
And the other one was 55, yes? So that means when I add the 2 together, assuming the volumes are additive, we'll come back to that later. What is my new volume? 90 milliliters. Oops. All right, 90 milliliters. What is in this 90 milliliters? How many orange things? No, just how many orange things? 6. Why are there 6? Because there were 6 over here. How many blue things? Why are there 4? Because there were 4 over here. I didn't add any things, did I? Okay. So the same number of particles are still present. They're just each in a bigger space. Okay? Now, this is where things start deviating from the actual question that we have up here. Whoa, wrong thing. Up here. Let's imagine there is a 1-to-1 stoichiometry. It's a reaction in which is a 1-to-1 stoichiometry. These things are all scooting around, and maybe these 2 run into each other, precipitate out. Maybe these 2 run into each other, precipitate out. Maybe these 2 do, and maybe those 2 do. You'll notice that we still have some things remaining, which would be the excess reactant, right? Okay, you guys get this, I think, pretty well. I'm just trying to get this little particulate thing going into your brain. Now, this one's a little bit harder to represent in a really small picture, so I'm not doing that because there is a 3-to-1 relationship, blah, 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 and they're ionic compounds that completely dissociate, so there's actually 4 separate things floating around in there when I first mix them together, which we've already done that little idea, I think, haven't we? Pictorially? All right. Anyway. Now, I'm asking you to determine the concentration of all the ions that were remaining. We listed them up here. And hydroxide. We eliminated one of them from our thinking. The hydroxide ion. Why? Because it was involved in the precipitate, and it was the portion of the limiting reactant. In fact, it is the hydroxide that limited the amount of product that could be formed. So we eliminated this from our thinking. Gone, see ya. We determined that the potassium ion and the nitrate ion were serving as what? Spectator ions. So however many particles there were to begin with, that's the same number of particles there were at the end. I think you guys get that now, right? Yes. Okay? But the problem is, there's a number, let's do this. Remember, this was originally potassium hydroxide. And when this dissociates, it's going to dissociate in what sort of stoichiometry? 1-to-1, right? So however many moles of potassium hydroxide we have is equal to the number of moles of potassium ion. The iron nitrate. Here's the moles of the iron nitrate. The nitrate, however, is going to be 3 times that amount. Would you agree? I'm not sure how I'm going to do that.
Why is 3 times the amount?
Because when the iron nitrate dissociates, I get that. So we have 0.0085 moles of iron nitrate, of which the nitrate ion is going to be 3 times that. So these are, I forget how I identified these yesterday, but let's go with this. These are the spectator ions. These are very easily determined as far as concentration is concerned, because all we have to do is take the moles of potassium that we have, which was 0.0099 moles here, divide by the new volume, which is 0.090 liters, and we get something. I don't know what it gets. 0.11? This is exactly where we left off yesterday, I believe. Now, what about the nitrate? Does anyone remember what the brackets mean?
The ion.
Concentration of, and in this class we're dealing with, unless otherwise specified, molarity. How many moles of nitrate are there? Well, there's a couple of different ways you can do it. You can either recognize that there's 0.0085 moles of iron nitrate times 3. That would probably be the best way to do it. And what's my volume that those moles of nitrate ion are in? 90 milliliters, or 0.09 liters. I'm not sure what that comes out to be. We know there's no hydroxide left. The only thing left is iron, but this is where it gets a little interesting, because iron was part of the
How much did I use in the reaction?
precipitate, and there was also the excess reactant. So some of it precipitated, some of it stayed behind in solution. I don't care how you do it. You can either think this through, or you can do some math, some stoichiometry. Doesn't matter. Currently, I'm going to guess that a lot of you would prefer to do the math because you're maybe not quite envisioning what's going on yet. Okay? So now we have to figure out how much of the iron was required. Well, the limiting reactant was the hydroxide. Okay? And we know that there is 1 mole of iron required for every 3 moles of hydroxide. Sorry, I just can't do that.
So we're finding out the iron that's required, right?
Yes. Except I shouldn't have done that there. My bad. I can do it one of 2 ways. You guys aren't going to like the way I can fix this. So let's not do it that way. How much iron is there? 0.0085 moles of iron present from that, we are going to subtract the amount that was required, which is going to be 0.0099 moles of, and this is why I was doing the math, what was it, hydroxide? Yes. And this, believe it or not, Gracie, interestingly enough, is where your brain was yesterday, about 4 steps before this. So, you guys are, I think, getting where this came, what this is here for. This is how much iron is actually there. We also know that some of it went away. That was easily accomplished by doing some stoichiometry. So we're going to subtract that from the quantity that's present. And then what are we going to do with that result? Yep. Now, some of the problems are going to present themselves in such a way that you can kind of do some of that in your head. The numbers in this case, well, yeah, you could have. 0.0033. Subtract that from 0.0085, you get 2. I lied. 5.2. All right, what'd you get? 5.8?
Yep.
Is this 0.0033?
Yes.
And we're subtracting that from 0.0085? Isn't that 0.0052?
Minus 0.0033 equals that divided by 0.09. So I can find the molarity equals 0.
Oh, and then this. My bad. Okay, you're right. I forgot to do that. What'd you get, 0.058?
Yep.
Iron. Okay. So there's those 3 answers. Now, I want to show you something kind of interesting, which hopefully, because I know early on when we were doing this dissociation thing, and some of you were kind of wondering why I had to put the charges on things. Okay? Well, what is the charge on the original solution of potassium hydroxide? What's the net charge of the potassium hydroxide solution? Well, don't we have equal numbers of potassium and hydroxide ions, so therefore the net charge is 0. What is the net charge on the iron 3 nitrate solution? 0. So if we combine the 2 solutions, shouldn't our net charge be 0? Right? Is it? And this is a good way to check if you did your math correctly, by the way. Some of you are looking at it going, I don't even know how to find out. Some of you kind of have an idea, but you're not really sure. Well, what's my total positive charge? You forgot something. Plus 0.11, whatever that comes out to be. Who are my math people?
Yeah.
You're not one of the math people? Oh.
Yeah, 0.11 plus 0.058 times 3 is 0.284.
0.284. Within significant figures, we're okay. because it's got a 3+ charge? Okay. Anyway, for those of you that get that, that's a nice little way to check if you did all the rest of this correctly. You guys need to practice this, don't you? Very good. Again, another reason why you have entire blank pages. So if you can turn to the nearest blank page, and probably I would use one that you can reference what you've already done. Does that make any sense? Which you may mean if you go backwards. I don't care how you do it. It doesn't matter to me, but I'm just trying to help you guys out. I forget who I was speaking to earlier today. Oh, now I remember. Someone said they have started the assignment and said they were crushing it already.
No, not me.
I know that.
I told you that yesterday.
Oh, I thought it was Madison that said it today.
That's really smart. Madison's not really smart. First off. No, Madison's not crushing anything. Besides my crushing your
I knew that was coming. Here we go. You know, because I know this is actually going to cause a lot of consternation really soon in the course, I'm going to go ahead and just start throwing this at you. Here's what I would like you to do. Here are the substances involved. Write a net ionic, notice how I'm saying this. Write a net ionic equation for the reaction that occurs for these two substances when they're mixed together. Write a net ionic equation for the reaction that occurs when these two substances are mixed. When solutions of these two substances are mixed. The reason I said it like that is, if you guys remember yesterday, I gave you a set of reactants in which there was no reaction because everything was soluble. Can I interest you in a crystal of copper sulfate?
That's mine. Stop offering to other people.
Well, you didn't want it.
I thought I was going to steal my itchy arm. He's like, tell me about my itchy arm. He's like, you want this? I'm like, can I rub it on my arm? He's like, no. Okay, what is it? Not something that helps your itchy armpit.
All right, what do we have?
Nickel 1 plus
Nickel what? Oh, gosh, my bad. Doesn't, I mean, it matters, but it doesn't matter.
Nickel 2.
Nickel 2.
Plus 2 hydroxide ions results in nickel 2 hydroxide.
There we go. That precipitates. Okay. Was anyone either there or headed in that direction? Good. Nicely done. Now, let's give you some quantities. What color do you want the nickel to be? I don't have purple.
Blue.
Okay, of the colors you have seen me use. Green. I heard a green.
Magenta. White.
And your choices are blue, black, blue. Okay, let's go with black. No, I don't want to do black. Sorry, blue. 63.2.
Is that 0.17 molar?
It is. And then the question that is not up there that I'm going to have you do, determine the concentration of any ions remaining in solution. So this is essentially exactly the same question that we just walked through on your own. Ready, set, go. Would you like to join over there? Would you like to join over there so you can talk to people? I'm just saying. Okay. Thank you, though, by the way. I'm guessing or hoping that you guys came up with these two quantities. Based on those two quantities, you should have identified this as being your limiting reactant. Even though the numbers are close, it's still, in my opinion, pretty easy. I need twice as much hydroxide. This isn't even 0.006 yet. And twice of 0.006 would be 0.012, right? So they're close, but you can still make the determination. Now, I know some of you feel more comfortable doing the math, and that's fine too. I'm just saying it can be done without doing that calculation. My bad.
I'm really confused.
I did it right, but I did it wrong.
Yeah, I was going to say, you used the right number, but not the
Yeah,
right.
right. Oh, yeah. Is that what you guys got for your mass?
Yep.
What are the species present? Which ion is not present in solution? The nickel. It's Gandhi. What are the spectator ions? Anyone done yet? Give me the concentration of sodium.
0.129 molar.
Yep. Molar is how you would say that, just like your tooth.
Okay.
Nitrate.
0.121 molar.
And hydroxide.
0.00714 molar.
There we go. Okay, on to gravimetric analysis.
By the way, would you say the limiting reactants 5 cents weren't hurt in the molars?
No, we wouldn't say that, Joe, because that would be dumb. You've been around him too long, haven't you? You knew that was coming. Joe, you haven't had too many opportunities yet this year.
No. You should have heard me in physics these past 2 days.
You've been on a roll? Mom have to say?
Nothing. Just talking to the soccer team because I finished my problem.
Did you get those answers?
I did.
Did you? You were listening? Okay, good. Good for you.
I think these are kind of fun.
I agree. And then my chemistry classes come in here and look at that, and I say, hey, at the end of the year, we're going to be doing this. And they're like,
Yeah, I feel like I can't quite get there without looking at this.
I know that, because this is your first attempt ever.
I got 0.129.
Yeah. What was the answer for nitrate?
0.181 molar.
Whoa, wait a minute.
What was it again? 191? 129.
And 0.0074.
I didn't get the first one. I don't understand why.
What's your final volume?
0.098.
Okay. How many? Oh, I know why. How many moles of nitrate did you have?
Oh, there's 2.
Yes. Which you see, I tried to sneak that in up there. So look, follow the green.
Yeah, and like I did that on here, like I put this.
Yeah.
I was looking at this paper.
You forgot to transfer it over.
Well, I didn't look at why it was the same
Okay.
number. But I just wrote it down.
Okay, so what's the limiting reactant? So, sorry about my bad. How much hydroxide ion is present initially? 0.0126 moles. Okay. Some of that ended up as a precipitate. Some of it ended up still. Some of it ended up still present because it was the excess reactant. Okay. So from that original 0.0126 moles, we have to subtract from that how much of the hydroxide was required. So you have to either do a little stoichiometry problem between the nickel and the hydroxide ion.
These two. Where I know, is that because that's like attached up here? Is that why it's got the number for iron?
Okay, start over. Point to the thing that you're wondering about.
This.
This number right here? Okay. We calculated, and you missed the whole spectator ion thing, and that's okay. So basically, this iron 3 is iron 3 nitrate.
Okay, so it's just like included, but.
Yeah, but the only thing that's actually doing any reacting is the iron. The nitrate is what we call a spectator ion.
Yeah.
It's just hanging out.
Okay, so then.
So whatever this is going to be the same as that.
Okay, and then. Like,
But since there are 3 of the nitrates, we have to multiply that by 3.
Okay.
Is that what your question was?
Yeah.
Okay.
Thank you.
Yep.
Is this the reason why I'm multiplying this by
Yes,
2?
yes.
That's the reason
Yep,
why. It
yep.
has nothing to do with this stuff.
No. The only time that stuff comes into play is in a mole ratio. Yep. All right. Again, the answers are in green next to the individual ions. Is anyone having any difficulty still getting those values? And about the only one that you might have trouble getting, if you're going to make a mistake, is the nitrate by forgetting to multiply the 0.00595 by 2. Chelsea? Okay. And then the hydroxide is because of the stoichiometry piece, which is where you are. So you've got the, you wrote down a really strange number there. That is not, no, don't do that. Don't do that. No. Because it's not by 2. Why did you, just out of curiosity, why did you multiply? Then, okay.
So
the only time we're going to deal with that ever is in a mole ratio.
Okay.
So you've actually multiplied it by 4.
Okay.
I'll bet your answer was twice as much as it should have been. Well, anyway. No, what's this .006? I'm not sure what that is.
That's what you had, except I just rounded it.
Don't do that. Why did you can't do that. You can't do that. Okay. How many significant figures are there?
Like overall?
In this value, how many significant?
There's
There's 1. How many should there be? Well, there's 3 here and 3 here. It's 350. You got to get in the habit of making sure you do that. Okay? So that's why this is the case. Okay? You're definitely going to have to make yourself do that. Okay. But anyway, once you've done that, you're going to be fine. You just multiply it twice. All right. We seem to have moved beyond. This is going to go bye-bye in about 13.8 seconds or less. If you would like to not have it go bye-bye, you have approximately 4.3 seconds left to take a picture. Okay, it's going. Next, everyone's favorite. This next type of problem, there are usually intentionally written. Okay, every question that has currently been presented to you has been very succinctly presented to you. You have this much of this much of this, find this. You may not seem like it was been succinctly said to you, but they have been. This next type of question that you're going to run into on occasion, they intentionally try to make it as befuddled as possible. Because this is life. You have to sort out the things you need and sort out the things you don't need.
I hate questions that give you full information.
So here we go. This next example is called the technique is called gravimetric analysis. The main reason it was called gravimetric analysis is because this is, in a laboratory sense, decades ago, before we had all these million-dollar machines that you take a small sample of whatever it is that you're analyzing, you stick it in the machine, it spits out some graphs, and you interpret the graphs and say, oh, it's got this much of this. Before, you used to have to do very similar to this. You had to actually chemically analyze everything by causing things to precipitate, and then you would measure the masses of the precipitates and do a little bit of mathematical magic to figure out the percent of a component of that. Hence, gravimetric analysis, because you were precipitating things out. Okay, so here we go. A good example of this would be a 0.4367 gram sample of phosphorite rock, which contains a bunch of ions that are listed there. Is to be analyzed for the calcium ion content. The calcium ion is precipitated. Now, a lot of times they'll give you how it was precipitated. By adding this and this and this, and it precipitates this. But it just says it's precipitated. By addition of water and oxalate ion, and then dried. The calcium oxalate monohydrate precipitate has a mass of 29.20. Calculate the mass percent of calcium in the phosphorite rock. Most of you heard this. Wah, 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 wah.
Calculate math.
Right. Percent.
I heard math.
Okay. Okay. Well, you can kind of see there is a lot of information in there. Would you agree? You got to dig out the things that matter. What matters? Well, what are we trying to find? The percent by mass of calcium ion in the rock. What's the formula for the rock? We don't know. We don't care. We don't care. But it does tell us what?
That it has the phosphate ion, the hydroxide ion, and the calcium ion.
0.4367. Gracie, I don't care. That's the total. When we're all said and done, when we're trying to find the percent, what are we going to divide by? The total. Okay? All right, we'll pick up there tomorrow. That's unfortunate. I would hate to see this chapter go this many